Okay, so what we do next, numpy set air all equals raise. So this is usually a good idea, so that in case we have any numpy errors, it's better to just throw, so it gives us the stack trace of where something went wrong. We'll define our normal functions, note to freak. Note, this one converts a MIDI note number to a frequency in hertz over 12, and just remember the order of operations. It's going to be 2 to that power times 440 basically. Okay, note, actually no, freak to note. That's our usual routine there. 12 times numpy.log 2 freak over 440 plus 69. Okay, that's the usual. Again, this takes the frequency of the fundamental pitch in hertz and gives us the MIDI note number as a result. And then some harmonics equals numpy.array. So we'll just do that. 1, 1. This is just for our tone generation. 0.1, 0.1. We just create some harmonics for, because every instrument has harmonics. So generate note. In this case, we don't really care what the harmonics are. We just want it to sound okay. So we can compare it to what we hear in the music file. Sample rate equals, we'll just give it the default, and samples is by default. Basically 44100 is in hertz. This is CD quality. It is supported by pretty much all audio devices nowadays. Harmonics equals some harmonics by default, but you can specify a different. Okay, n0 is int numpy.round note number. So we're just rounding it. We don't absolutely have to round it. We can generate some out of tune notes as well, but in this case we're just samples equals numpy.zeros, and we could also call this tone generator, but it's and samples. Okay, so we tell it to create an array with all zeros and samples in it. The type is numpy.int16. Okay, just when we feed audio to the sound device, it wants 16-bit signed integers, also known as shorts. Times is numpy.linspace. Just creating a new variable. So this one will create, we'll say start at 0, and then the last value should be samples.size over sample rate, and then the number of samples is samples.size. Okay, so far so good. So this will create a number of timestamps, and just my personal preference, I'll just put the closing parenthesis on the new line. Okay, and then the other thing is we will need to scale it, scale factor. Basically, we want the note to be loud enough. So anyway, scale factor, actually this is divided harmonics.sum. Okay, so the divided by harmonics.sum is just a normalization so that we don't have clipping. So we're going to go through all the harmonics for I in range, len harmonics, and then we do nmult equals I plus 1. So this is really, nmult is a multiplier. We do freak equals nmult times note to freak and 0. If you remember about harmonics, you take the fundamental pitch, you convert it to a frequency, and then you do whole number multiples, where, you know, so in this case we start at, I starts at 0, so nmult starts at 1. So, you know, 1 times the fundamental frequency, 2 times the fundamental frequency, 3 times the fundamental frequency. Okay, so phase is 2 times, and each time all those different frequencies, each one has its own loop iteration. So numpy.py times freak times. Okay, so these are the time values times, you know, 2πf, you know this from physics class. Wave equals numpy.exp 1j times phase, so exponential, times harmonics I. Oof. Okay. don't like that scroll bar. I'm gonna make it do that. Actually, we're not gonna use this space very much, so I'll just make it a little bit wider. Okay. So samples, everything, actually plus equals. We don't want equals, we want plus equals because we are adding the different harmonics components to this. So scale factor times wave.real. We're just the exponential, the exp is going to give us cosine and sine. We'll just take the cosine in this case, the real value. And then dot as type numpy.int16. So remember, you always want that. You always want int16s. And then that's about it. Basically, the scale factor takes care of normalizing it, and then you just return samples. So that would be it for this function.